Good morning, students. So in the last module we were discussing about the oxidations by using lead tetraacetate. We have discussed two applications, that is oxidation of vicinal diols as well as oxidation of primary as well as secondary alcohols. And in the primary alcohols we have seen that by using lead tetraacetate, primary alcohols can be oxidized into your aldehydes. Now, primary alcohols undergo oxidation. Primary alcohol undergo oxidation to give aldehydes by using lead tetraacetate. Now, this oxidation of primary alcohol into aldehyde is possible provided the primary alcohol is not having any delta hydrogen atom. Because if you are having only one alcoholic group containing delta hydrogen atom, then instead of converting it into aldehyde, there will be abstraction of delta hydrogen leading to the formation of a cyclic ring to give you a 5-membered cyclic ring as the product. Say for example, if I take a primary alcohol having delta hydrogen, so this is alpha, beta, gamma, delta. So we have a delta hydrogen present in it, then this undergoes oxidation by using lead tetraacetate to give abstraction of delta hydrogen. So you can see this is alpha, beta, gamma, delta. So delta hydrogen will be abstracted to give you a 5-member ring which can be called as a tetrahydrofuran ring is formed as the product. So let us see the mechanism, how the reaction occurs. So if you see the mechanism of the reaction, primary alcohol as usual undergoes oxidation by using lead tetraacetate. Similarly, elimination of acetate ion to give CH3, CH2, CH2, CH2O lead with the 3 acetate ions. And this acetate ion reacts with the hydrogen to give acetic acid as the product. Now this, under normal conditions, we know the abstraction of hydrogen will take place to give you the product. But when you have a delta hydrogen, the reaction will be different because this has a hydrogen atom. So this is a delta hydrogen atom. So this delta hydrogen atom will be abstracted by the acetate ion and this attacks the oxygen with the loss of lead acetate. So it forms lead diacetate plus acetic acid with the formation of a 5-membered ring, that is furan ring is formed as the product. Okay, so this is how the reaction occurs when an alcohol having a single OH, that is primary alcohol, with a monohydric primary alcohol with delta hydrogen atom. Now if the same reaction containing your delta hydrogen atom, if this is treated with lead tetraacetate in presence of pyridine, that is in presence of pyridine which is acting as a base, then the product will be the normal aldehyde. The reason is, in presence of pyridine being a base readily abstracts the hydrogen from the alpha carbon rather than the abstraction of the hydrogen by acetate ion from the delta carbon atom, leading to the formation of aldehyde as the product. So, the oxidation by LTA for the monohydric alcohols, if you want the aldehydes, it should be carried out only in presence of pyridine. In the absence of pyridine, you will always get the cyclic ring as the main product. So, that is about the oxidation of lead tetraacetate with primary alcohols or the secondary alcohols. We know that in secondary alcohols, it always results in the formation of ketones. Now, let us see the oxidation of lead tetraacetate. Oxidation by lead tetraacetate in the olefins containing allylic hydrogen. Olefins containing allylic hydrogen means, say for example, if I take 1 propene, this is your allylic carbon. The hydrogens containing attached to this carbon can be called as allylic hydrogens. So, this when treated with lead tetraacetate, allylic hydrogen undergoes acetylation or oxidation to give an acetyl group substituted by an acetyl group. So, this is called as the oxidation of allylic hydrogen to an acetyl group. So, if you see the mechanism how the reaction occurs, so the mechanism of the reaction can be given as olefin with allylic hydrogen reacts with lead tetraacetate. Lead tetraacetate with the loss of the hydrogen to form an acetic acid. So, it gives CH2 double bond CH, CH2 with 3 acetyl groups. Okay. For the sake of convenience, I am writing one of the acetyl group like this. Now, this undergoes acetylation at the allylic carbon by the donation of electrons with the oxygen like this. So, this results in the formation of CH2 O, C double bond O, CH3, this is your terminal carbon, then CH double bond CH2. So, you can see the allylic carbon undergoing acetylation with the loss of lead diacetate. Okay. So, in this way, whenever you have an allylic hydrogen, it undergoes a reaction at the allylic carbon with acetylation. In the absence of allylic hydrogen, this reaction cannot take place because this reaction occurs due to the acidic nature of allylic hydrogen. Since this is due to the acidic nature of allylic hydrogen, so any acidic hydrogen present in a substrate can undergo similar type of acetylation reaction. Say for example, if you take a carbonyl compound, we know that the hydrogen attached to the alpha carbon of a carbonyl compound is acidic. Therefore, when this is treated with lead tetraacetate, it undergoes similar reaction giving rise to the acetylation at the alpha carbon which holds your acidic hydrogen to form acetyl group with the formation of lead diacetate and acetic acid. This is formed as the product. So, if you see the mechanism of the reaction, how the reaction occurs in case of the acidic hydrogen, say for example, if I am taking the same acetone as an example. We know that the acetone can exist in the tautomeric form in the form of enol. It exists in the form of an enol. So this can react with lead tetraacetate. Lead tetraacetate with the loss of COH. So this is loss of acetic acid leading to the formation of CH3, C double bond O, CH2, O, acetate. So the reaction occurs in a similar manner with the loss of lead diacetate and the attack of carbonyl oxygen on your CH2, giving CH3, C double bond O, CH2, O, C double bond O, CH3. So you can see the acetylation being taking place at the alpha carbon atom. So the acetylation is possible either at the allylic carbon, which is due to the acidic hydrogen, or your acidic hydrogen which is attached to any electron withdrawing group can undergo similar type of acetylation reaction, which can be called as alpha acetylation by using your lead tetraacetate at the allylic hydrogens or at acidic hydrogens. Now another application of lead tetraacetate is decarboxylation of acids. Decarboxylation reaction of acids. Say for example, if you have a carboxylic acid, this undergoes oxidative decarboxylation to give an olefin as the product. So if you see, by using lead tetraacetate, if you see the mechanism of the reaction, carboxylic acid reacts with lead tetraacetate involving loss of acetic acid to form there is an oxygen here. This is the intermediate that is formed. This undergoes oxidative decarboxylation by the loss of carbon dioxide like this. This is the carbon dioxide which is being lost. This is lead tetraacetate which is being formed. This is abstracting the hydrogen from the beta carbon atom with the formation of carbon-carbon double bond, leading to the formation of an olefin plus carbon dioxide plus acetic acid plus lead diacetate is the product. So in this way it undergoes oxidative decarboxylation. So in case of oxidative decarboxylation, there is always loss of the carbon dioxide in the form of your carboxylic group as well as the loss of the hydrogen from the beta carbon, leading to the formation of a double bond at alpha and beta carbons of your acid. So decarboxylation of acids leads to the formation of an olefin as the final product. Now we will see the other applications of lead tetraacetate. The other application is the oxidative decarboxylation of 1,2-dicarboxylic acids or vicinal dicarboxylic acids. 1,2-dicarboxylic acids means if you have two carboxylic groups present at the adjacent positions, it can undergo oxidative decarboxylation to give a alkene as a product. Say for example, if this is a 1,2 means having carboxylic acids at adjacent positions, this is reacted with lead tetraacetate, it undergoes oxidative decarboxylation with the loss of 2 molecules of carbon dioxide to give an alkene where a double bond is formed at the 1,2 carbons holding your carboxylic groups. So let us see the mechanism of the reaction. If you see the mechanism how the reaction occurs, let me write this as R. I am writing the adjacent carbon, that is these two carbons, as R groups. Okay? So this reacts with lead tetraacetate. Lead tetraacetate. The oxygen donates its 2 electrons to lead, and the loss of proton from your carboxylic acid to form an acetic acid with the addition product with the carboxylic group to give lead acetate So this undergoes the cleavage through the formation of a cyclic transition state. You can see the carbonyl of the acetyl group of lead tetraacetate is abstracting the acidic hydrogen with the loss of carbon dioxide, one molecule of carbon dioxide, second molecule of carbon dioxide, okay, with the formation of lead diacetate and an acetic acid molecule here. So this leads to the formation of R, C, double bond C, R. plus loss of 2 molecules of carbon dioxide plus 1 molecule of acetic acid from the lead tetraacetate and lead diacetate. So in this way, a 1,2-dicarboxylic acid can be converted into an alkene. So the only requirement is the 2 carboxylic groups should be present adjacent to each other. Even a tri or a tetra or a mono substituted 1,2-dicarboxylic acids can also undergo similar type of reaction to give the complete decarboxylation to form an olefine as the product by using lead tetraacetate. Another important application of lead tetraacetate is acetylation of olefinic double bonds. Acetylation of olefinic double bonds, which is, we can say, oxidative addition at carbon-carbon double bond. So if you have carbon-carbon double bond reacting with lead tetraacetate, it gives rise to addition reaction with the addition of 2 acetyl groups. Addition of 2 acetyl groups. Now such a type of reaction is possible provided the olefine is not having a alpha methyl or a alpha methylene or a alpha methine group. Because if you have alpha methyl, alpha methylene or alpha methine group, it means that it is having an allylic hydrogen, and in presence of allylic hydrogen, it undergoes allylic oxidation rather than the oxidation at the carbon-carbon double bond. So if you see the mechanism, how the reaction occurs, mechanism of the reaction, carbon-carbon double bond reacts with lead tetraacetate. As usual, lead tetraacetate acts as a electrophilic reagent. So the olefinic electrons, double bond electrons, attack on the electrophilic lead with the formation of carbon lead bond. This carbon gets a positive charge, so this will be attacked by the acetyl group, leading to the formation of acetyl addition on one of the olefinic carbon and the addition of lead on the second carbon atom. Then this undergoes intramolecular substitution reaction, which can be called as intramolecular nucleophilic substitution, where the carbonyl oxygen is acting as a nucleophile with the attack on the carbon with the loss of the lead diacetate. So this forms the addition of acetyl group on the 2 olefinic carbons with the loss of lead diacetate as a product. So in this way, the acetylation occurs at carbon-carbon double bond. But this reaction is possible only in the absence of alpha hydrogen atoms. In the presence of alpha hydrogen atoms, it becomes an allylic hydrogen. So it undergoes preferential oxidation when compared to the oxidation at the carbon-carbon double bonds. And the last application of lead tetraacetate is methylation reaction. Methylation at aromatic hydrocarbons. Methylation at aromatic hydrocarbons. We all know that aromatic hydrocarbons undergo electrophilic substitution reaction, but in case of lead tetraacetate, the methylation reaction is not an electrophilic substitution, rather it is a free radical substitution reaction where a free radical methyl is generated from lead tetraacetate, which reacts with the aromatic ring to form a substituted product. Say for example, if you take lead tetraacetate, this undergoes cleavage, that is homologic cleavage, to form lead diacetate and 2 molecules of acetyl radical will be formed. Acetyl radical formed undergo decomposition with the loss of carbon dioxide. So there is a loss of carbon dioxide with the formation of methyl radical. Now this methyl radical reacts with your aromatic ring. So if I take an aromatic ring, this reacts with methyl radical. Methyl radical acts as a electrophile. In a similar manner, free radical substitution occurs in the aromatic ring, giving rise to the substitution of methyl group. This can react with, the methyl group can react with either your acetyl radical or the methyl radical with the abstraction of hydrogen to give the aromatization back. So you will get substituted product with methyl with the formation of either acetic acid or methane is formed as the product. Now this reaction, that is a free radical reaction. So this free radical reaction occurs only when you have a lead tetraacetate and an aromatic ring in presence of acetic acid. So these are the various applications of lead tetraacetate. So we have seen that the lead tetraacetate can give the various types of applications, that is your oxidation of vicinaldiols, alpha hydroxy acids, or your primary or a secondary alcohols, or a carboxylic acid. So you have several applications of lead tetraacetate, but the most important application of lead tetraacetate is oxidation of 1,2-diols or vicinaldiols, where the reaction occurs by oxidative cleavage to give the carbonyl compounds. So this is the important application of lead tetraacetate. Though other reactions can also be used, but this is the most important application of the lead tetraacetate to give the carbonyls from vicinal diols. So with this we finish the applications or the oxidation by using lead tetraacetate. So in the next module we will see the other oxidizing reagent. Thank you.